Hello, ladies and gentlemen, boys and girls. I am Natanis Likens, and this may be the very last video that I ever make. We'll see. My channel's effectively dead. I don't have time to actually make videos anymore. So yeah, this is just gonna be like a one-time deal because we only have like 95 subscribers, and I feel like I can test the waters on stupid stuff. So we're gonna do that right here, right now, because I guarantee you, there's gonna be some hecklers saying that I don't know what I'm talking about and blah 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 blah, and you're an idiot. That's all I'm gonna say. So you need to talk about a few things that have been on my mind within the science world. But before we do that, I know like we don't have any credibility with any of those people. So I want to kind of point out some things. And yes, we are in Minecraft. We are in a video game. You just bear with me on that a moment. So this is a segment display that I made. I made this, okay? I looked at this display and I created it. This is not originally mine. Like, I saw how somebody did this, and I effectively just copied that and then had to figure out everything else from there. So this portion up here, this is all like somebody else's. I don't know whose. Everything else, all of this is mine. Okay. And the reason I'm trying to point this out is to like show the level of intelligence that I had in order to figure out all of this. And this is something that I did like a long time ago. Long time ago. It was part of an idea that I had for making a battleship style game inside of Minecraft using redstone. And I was told that there's much better ways to do it, but whatever. This was a fun project. I had a lot of fun doing it and thinking it up, and it was just absolutely insane that I even got this to work. Uh, we're going to try this real quick to just demonstrate, but I do know that part of it is broken. One of the updates since I made this has broke the whole mechanism. So we will see if we can get this to work. So we put this in spot 6 of magenta. So we go to magenta and we find spot 6, and it should light up, hopefully, if everything is actually working. Oh, yep, there it goes. Now it is backwards because I did the setup incorrectly, but you can see right there we got spot 6 lit up on the magenta line. So yeah, all of that was me figuring it out and trying to troubleshoot and everything and figure out like what I needed to have happen and everything. There's probably a better way to do it, and now that a lot of time has passed, but I haven't really felt like picking this project back up because, like I said, somebody said that there's a better way to do it than this monstrosity, and you would actually need 2 of these monstrosities in order to get this to actually work, and I really don't feel like doing that. So yeah, that should give you an idea of the level of intelligence that I have. We're not going into how the redstone actually works. Just know that it detects where it is on an X. It detects where it is in the grid, and then sends a signal out to that specific spot to activate that light. Now, there is a couple of problems with it. One is that we're just going to say that this is an x-axis and this is a y-axis. Okay, I know that's not correct, but we're just going to say it. So on the x-axis, you can only ever have one instance of it. So for magenta, we have our one instance. We cannot have another instance. It will not work. Same goes for the y. On the 6 line, we will never be able to put another 6 on here. So we can do one of every one of the colors. Pretty much we can only do one of all the colors because there's too many spots as far as the numbers in order to have multiple of these, but we can do one of any of the colors and activate that. Again, it is hooked up backwards, a mistake that I didn't realize until I was done. But yeah, it's insane that going through there. So it sends out a signal over to these pistons. These pistons push sorry, these pistons here push down and pull up their, sorry, this one pushes up. It's been a while since I've even looked at this. I got to remember how it works. So this set of pistons here pushes the wool up, and when a signal comes through on a specific line, it goes into this here, which sends all of these at once. However, because we're only activating one piece of wool at a time, only one line will light up, only one will get pushed. So you can see basically it's decoding the X and Y over there up here. That's basically what's going on. That's why we got this one redstone block sending the signal out there. And if I go here and we get rid of that, it should deactivate it. Well, it should. Like I said, a recent one of the updates has created some bugs in the system. So it should reset it, but clearly it's not resetting it. Oh yeah, this thing's royally broken now. Yep, it's busted. I'll have to figure out what's going on there at a later date, maybe. Again, this is a project that I don't really feel like continuing. Anyway, let's move on. Just to demonstrate a little bit more before I talk about what I want to talk about. And again, it is really heavy science stuff. So first off, we're going to talk about where all this came from. What is this? I kind of got a little bit of a demonstration over here. So there's a Minecraft YouTuber named Tango Tech. And in one of his videos of the past, I forgot how old the video is. Like it's been a couple years now, at least two. He built a factory in vanilla Minecraft where these crafters will produce whatever he has assigned to it. And the entire system uses binary in order to call for a certain item. So in this instance, I've got stone there, but I never really completed this. I was just trying to recreate what he did from what I could see in his video. And there was very little that I could see. So I was trying to figure out, like, how do you take the signal coming from here and transform that into a binary signal that will only read one time? Uh, with what he showed in his video and what I could gather, it's not correct. But then again, like he didn't show the whole thing, so don't hold me to that. I don't know if it's correct or not, and I haven't downloaded the world to go take a look. Uh, anyway, so that's what this is. This is me trying to reverse engineer it, and I actually did it in the wrong order because his system is sending out a signal as the call. This is actually sending out a signal as the activate. So instead of instead of this something up here sending a signal down through this, this is actually sending a signal up through here. So it's actually backwards what he had going on. But I did figure it out. And no, I do not have any kind of knowledge of computer science like that. The most that I know about binary is that it is a counting system that basically just increases as you go. That's it. That's what I know about binary. And yes, the system works. So how does it work and why does it work? So one of the things that I said just a minute ago, one of the early problems that I had thinking about how to get this to work is how do I keep it from reading anything as belonging to a certain group if any part of it is the same. So for instance, on this line here, this is the number 4. So anytime an instance of 4 pops up, how do I make sure that is not something that is not one of the others? Like we got 4 choices here for the number 4. how do I make sure that only one of these is being activated? That's the question that I had to ask myself is, once I get it encoded, how do I decode it and make sure that only one instance of something is activating? And that's where my system is very different from his and a lot more complex, because I still don't fully understand like how he's decoding. I understand how he's encoding, but there's nothing, the way he's done it, there's no way to decode it. So the main problem that I had was, once I've got something encoded, how do I keep it from activating something else, like activating something it shouldn't? So we got 4 instances of 4 here. I only want one of these to activate, like this line here. I only want this one to activate. That one, this one, and that one should all stay off. How do I do that? That's where this whole system came in. And we only have up to 25. I did program this so that you could do it up to 256. Actually, it'd probably go further than that. I think it would be like 500 something. I'm not doing the math off the top of my head, which I believe would be like 511, because I don't think it would do 512 because we only go to 256 on that. But we do have 25 units up here, and I can demonstrate it. So we got a redstone lamp in these corners here that will turn on anytime I activate this a specific spot. This one, there's no lamp here. This is actually, it's connected to one of my creations for how to make a given item with the crafter that is not a bare bones basic recipe. That's my own creation. That's not what somebody else did. And so is that one over there. Anyway, so I can activate pretty much any one of these 25 just by inputting the number for it. So let's go ahead and demonstrate this. We'll do 1 and then we'll do 25. So 1 is activated. We'll send the signal out. And the signal is going to come up here and you'll see that this is blinking. And I can go down here and turn it off and you'll see that it will turn off. So now these aren't blinking. Don't worry about what the blinking is for. This was a demonstration. I figured, hey, this would be a perfect thing to use it for. So now we can go to 25 and turn on 25. So 16, and just remember that binary is effectively just adding up a certain amount. So 16, 8, and 1. And you can actually watch all the lights go turning on and everything, and watch it going through everything. And look here, number 25 is active. You can see that this is spot 25 right here, and that redstone lamp is on, and none of the other redstone lamps are activated, even though you can see that the copper bulbs are activated. So again, this was my way of figuring out how to decode all of this. Again, this is to demonstrate the level of intelligence. Nobody showed me how to do this. I figured it out on my own. And it's a lot of computer science things that I just figured out. Like, I didn't learn this anywhere. Point in case, like I was talking to a coworker friend of mine about this here. This is computational redstone. That's Matt Batwings had a video on. I was learning a little bit of it and I was going to use it and everything, but more or less I wanted the and or gates in order to like progress with some ideas that I had. So and gate, simply put, you turn this one on and that one to activate that lamp there. If either one of these are not on, that lamp will not stay on. Both of these have to be on for that to activate. Again, that is a circuit that I needed to learn. I didn't know how to build the circuit. I understood like what this does and everything. I just didn't know how to build the circuit to do that. Same thing for this one. This is a OR gate. So you got this one, it'll activate that lamp. That one will turn it off. So both of these are on. We can't have both of them on. I can turn this one off. You can see that that lamp has now turned on, and we can have like either one of these. So if we get a signal from either of these, it turns that lamp on. But if we get a signal from both, it doesn't work. Again, a circuit that I needed to know. This is, I don't remember the exact name of it, but this is like one of the big things in computational redstone that somebody else came up with. Not Matt Batwings. this is not his creation, this is something else. But basically, this is a data storage. It's another form of binary that I kind of like, kind of don't like. It's very simple to understand. I say that because my coworker, my former coworker slash friend, didn't understand it at all. It's very simple. Let's go ahead and turn this off. So we got that light on down there, and you will see that every one of these is turned on, okay? So I can come in on this line, and I can turn them off at any given point. Let's just go ahead and do kind of low. Let's turn it off there. So we only got 3 lights lighting up. Why? I don't know. I haven't been able to figure out why this one is lighting up. That shouldn't be doing that. Or more correctly, probably the bottom one. I don't remember. One of those should not be lighting up. I don't know why it is. So basically what has happened is we have interrupted the signal and created an on-off area. So we're effectively encoding like this signal here. We could create a set of signals here. So I can come in over on this side again, and we can come back and do another one. Let's just go ahead and do that one. And then we can come up, let's go here. So we got another set of 3 going on, and then should be that. And do that one. That's not going to be 3, but see, again, I don't know why the ones below are actually getting activated, but they are. So you can kind of see like where we're going with this. Like you can encode it like that and everything. And it's very simple to understand what's going on. So the comparator is just comparing strength, and it's saying which one's stronger. Let me get some blocks here. So just to make it simple, and yes, I understand that this is not like anything else. If we have a signal strength of 3 coming in, and there's another line coming in to this side, while this is in addition, or is it? No, it's an addition. While it's an addition, it's going to basically compare these 2 signals, and whatever the signal strength is on this side is going to compare to what it's getting back here, or vice versa. You could say it either other way, but basically what you need to know is if the signal from the back side of this is stronger than the signal from the side, the signal is going to go through. Now, we got 3 here, 3 is more than 1, so the signal would go through here. Here, let's do it this way to just kind of explain this a little bit better. So we got 1, 2, 3. Well, this is going to be backwards of what I was just saying, but you'll get the idea. So we got a signal strength of 3 going into that. Well, really, it'd be a signal strength of like 12 going in there. And 1, 2, 3, 4, 5. So this is a signal strength of like 10 going in there. Off the top of my head, I do believe that is 10. I wish I had the data pack that shows that, so I know exactly what it is. But you'll see that this means that, if I can hit the right button here. Let me find this. So that, yeah, that should be going through. That's fine. That's fine. That's fine. So basically, this signal is stronger than that, so it's turning on the redstone lamp. Now, if I go up here and I put this in, you'll see that this is a signal strength of effectively 15 right here. So 15, 14, 13 going into that. This is a signal strength of 14. This one is stronger, so it's not going to turn on this redstone lamp. Okay. Now, again, we can go out this way, and you'll see that that has no effect on it. This signal strength is still stronger than that. So anytime we overwrite the signal coming in from a previous line, we can kind of demonstrate that again here. Not in this fashion, but here. So this signal strength is going to be 15, 14, that is going into this comparator, which is turning on that redstone lamp. Now, if I turned on this one, it would be like 14 as well, which would turn that off. So let's just go to the next layer. So 14, so 15, 14, 13, 12. Now, we've got this one on right here, so we've got a signal strength of 14 coming into the side. This has a side of 12, that is why this is shutting off. Wrong button. Very simple thing to understand. Now, the friend in question, this is why I'm bringing this up, the friend in question didn't understand this. I know I'm doing a horrible job of explaining it. I am not a teacher. Okay, I am not a teacher. I don't know how to like make it sound simplistic. I just see it as simplistic. I fully understand what's going on here. You're effectively just creating a number and then seeing if the other number is higher or lower. That's it. That's all that's going on with the comparator. Basically, this is computer science type stuff, and he was completely lost. And I was watching the video and just understood it completely. Now, it again, I never had any kind of training or anything on that, and this is like very simple for me to understand everything. So what does that got to do with anything, and what does it got to do with whatever I want to talk about? The point of all this was to show the level of thought and understanding that I have that is far beyond my actual training, my actual knowledge, and everything. It's far beyond any college that I've ever had. I took graphic design and programming in college. I didn't take any computer science like this, like binary and things. So they didn't teach us that in Java 1, which is the most that I've taken. Java 1. Yep, that's it. That's all I've ever taken is Java 1. The most complex thing I've ever taken is Java 1. Well, I took C++, but I don't really count that because I didn't pass the class. I got obsessive on one of the assignments and I couldn't figure it out. I still to this day don't think that what she was asking for is possible. I think I could have broken anybody's program in that entire class. Simply because I was like, that's not possible. You can't do that. And because I had worked on it and worked on it and worked on it for like months, and I just could not figure out how you could keep the program from not crashing. Uh, it was statistically impossible for the program to crash. The problem is that it could. That's where I was getting hung up, is how do I keep it from not crashing? Yeah. So enough about that. What does that got to do with anything? Let's talk a little bit about some other things, because one of the reasons I wanted to do this is something I came across a video a while back about a debate, or the great debate between Einstein and Bohr. And if you know what I'm talking about, well, get ready for a doozy, because again, I probably have no right to even talk about this, but we're going to talk about it. I gotta find some colors here. I'm not sure which one of these I want to use. And the great debate, if you don't know what I'm talking about, Bohr, I don't know his full name, so I apologize in advance. Again, knowledge level is not on that high of a level. The thing that I wanted to point out with all the redstone stuff is my level of understanding. Yes, my knowledge is lacking. I will admit that first and foremost. It's my ability to understand things and read things that is really what I want to try and overemphasize here and point out, and then talk about some of this stuff. So the great debate was, it had to do with quantum mechanics and specifically quantum entanglement. And that's why I've grabbed some blocks. So the idea of a block, we're going to use green and blue for this part. We're going to use green and blue for something else here in a minute, or green and red for something else here in a minute. So the idea is that when you got two particles, they are quantum entangled, and they are always the opposite of each other. Okay. This is not the main thing that I wanted to talk about. I'm off topic. I'm going with this first. I want to try and point out something, because they recently said that Bohr was absolutely right. Okay. So here's the thing. When they go to check when they go to inspect it, that's when they're finding information out about this. And Einstein was like, that doesn't make sense. That breaks all of general relativity, and it creates paradoxes. Basically, what is happening is they don't know what the two particles are doing until they measure them, which suggests a lot of ridiculous things, because if the two particles, you don't know what they're doing until they are measured, and they're always doing the opposite of each other, that means that these two are communicating information across distance in an insane speed, or at an insane speed, which created paradoxes. I'm not going to dive into the paradoxes and what that problem is. What I want to talk about is why Einstein was actually right on this particular thing and what is going on. So Bohr and all the quantum physics people who came up with this were just like, this is how it is. We don't know what these two particles are doing until we measure them. And if you measure them at any kind of distance, that means it's transferring information between the two entangled particles at insane distances, which creates a lot of problems. And it means that these two things are exchanging information faster than light, which Einstein said is not possible. And Einstein was like, so either there's some kind of spooky action, that's where we get spooky action going on, or there's something else going on. And that's kind of where I want to talk about, that there is something else going on. I'm just surprised nobody's realized it. So we're going to do this real quick. I'm going to do a little setup here very quickly to kind of, well, we don't really need that much. Let's just go with 3. So how are they measuring this? Okay, so they came up with the idea, in order to measure these particles and see what they're doing, that they would take 2 magnets. Okay, we got red and green. So one of these is positive, one of these is negative. We'll say that the green is positive, and we'll say that the red is negative for now. It honestly doesn't matter which one's which. I wish I had done a little bit of a setup before now, but I don't think anybody's going to watch this, so whatever. Anyway, so we got 2 setups exactly the same here, and this is how they were able to measure them. So we got a point back here where the 2 pairs of entangled particles were being created, and they were sent through these sets of magnets. And the way you would measure them and figure out which one's which is by their displacement, like what direction do they go? Because if it's a negative particle, it's going to be pulled towards the positive. I don't remember what I said. So red is positive, green is negative. So if we've got a negative particle, it's going to be pulled up, like up at an arc, because the opposites attract. And if we have a positive particle, it's going to be pulled down because, we got negative here. So that is how they were measuring them. And this measurement is happening back there. And until they measure this, they don't know. Okay. Does anybody see the problem with this? Does anybody see the problem? Please tell me you see the problem with this. And we're not even going to talk about the alternate experiments where people are making alterations to it, because they came up with the idea to test whether or not Einstein was right by rotating these and seeing if the disagreement between the 2 pairs was the same. And we're not going to get into the details of the disagreement. I'm just going to ask you, do you see the problem with this? If we don't know if it's a negative or positive particle before we measure it, they shouldn't move. If this particle, before we measure it, and they're saying that we don't know what this particle is until it gets back here and we actually measure it, it shouldn't move. Okay? If that particle is in fluctuation, if it's going between positive, negative, this should be just a straight line shot. You shouldn't see any displacement. So, yeah, I'm surprised nobody's really realized that. That shouldn't move, because if we don't know what it is until we measure it, then passing through these magnets shouldn't matter. It should just go straight through, and then, oh, I'm going to decide to be this. Well, it still should be on the same path, but because we're measuring which direction it goes and determining whether or not it's positive or negative based on what magnet it was pulled to, that means before it freaking got into between the magnets, it already decided. When it's back here, it has already decided what it is. Actually, let's put it up high compared to the blue. It's already decided back here what it is. And the easiest way to explain why that is simple. We are taking a pair of particles that are stuck together and splitting them. The moment we split them is when we decide. Now, when the particles decide. Now, this could be either or. So it could have been this, it could have been that. I want to make that clear. It can be either one. And in fact, in this machine, like sometimes it would be this arrangement, okay? And then that would make this, and this. It doesn't matter which way it is, okay? That's the point I'm trying to make right now. It doesn't matter which one of these is. The moment it is split is when it actually decides, like, I am positive or I am negative. So that is why Einstein was actually right, that it happens at the moment of the split and not beforehand. Again, if this particle is still in fluctuation until we measure it, it should still be going straight through at the same angle. It shouldn't be getting displaced by the magnetism of the two magnets because it hasn't chosen yet. Now, you want to argue with me on that and say that no, that spooky action is still a real thing. They're communicating at distances with no, they're not. The easiest way to actually show that is to understand that if this is only a certain positive or negative particle, and that's not exactly correct, I understand that. It's a proton or a neutron. I don't remember exactly which. The only way that you'd be able to actually measure that is if you had another machine back here. Another set of measurements. It's not passing through another magnet. And bear in mind that you would actually have to be catching this at the same angle that it left. So the only way that you would be able to do this is if you had another machine back here that is also going to measure this. And remember that this displacement, this is going to go like, this is probably going to be up here now, and this one is probably going to be down here now. So it'd have to be at the right angle so that you could catch it. And the only way to prove that Bohr would be right or Einstein would be right on this, if you're still fighting with this, because turning this thing, that's not going to do jack. You're just changing the angle that's getting displaced at. That's all you're doing. You're not, even if you're looking for a certain disagreement in the directions of the two pairs, it doesn't matter. Okay. There is a scientist that did this. He turned one set of these to see if the displacement held true or if Einstein was right. His results actually showed that Bohr was right. But again, like, turning this thing doesn't matter. What you need is a setup that can measure both of these again. And the only way that you would prove that Bohr is right, if this is deciding if it's positive or negative only when we detect it, that means that as it's flying through, it's changing again. So if you had another machine back here to catch the particle again and detect it again, eventually, if there is, this particle is changing all the time, eventually you should find that this pair is no longer the same thing. Like, it was negative here and now it's positive. It was positive here and now it's negative, but they're still the same. They are going to be the same, because the moment these two are split is when they are actually decided. There's no debating this. Like, the moment they are split, that's why these magnets are activating and pulling them in certain directions. It's not going to just randomly change back here and then be like, oh, I'm positive, so I need to be up here. No, that's not what's happening. And there's no kind of spooky connection going on. There's nothing that is like passing information through a nothing medium. In order to transmit any kind of information, it has to pass through something. When you're talking about particles this small, that information is not passing through anything. So there's no way these two particles are still communicating. They stopped communicating once they were split. And again, once they are split, they're whatever they are. Okay. Moving on from there, we got to talk about something else, because this is something that has been bothering me and bothering me and bothering me for years. It has frustrated me. And that is the very notion that gravity is its own entity. And they are trying to find. I didn't watch the full video because I got annoyed with it like 30 seconds into it. But they are trying to find the graviton particle. And the graviton particle is apparently hidden, and it'll prove science right, and it'll be what bridges quantum mechanics with general relativity. And no, you're not going to find a graviton particle. Gravity is not its own thing. And what I mean by that is, you're not going to go out into space and just find a pocket of gravity where there's nothing. Okay, you're not just going to find gravity just floating through the void. Gravity is a byproduct. Gravity comes from somewhere. It comes from something happening. What exactly that is, I'm going to leave that up to debate. And I want to start off trying to explain this by kind of pointing out a couple of things that have happened in history, one more recently than the other. The first one is going to be, we got to talk about Neil Armstrong and the moon landing. So, if you don't know, there is an interesting fact about the moon landing where the two astronauts, Neil Armstrong, and honestly, off the top of my head, I don't remember the other one. I'm sorry, I am horrible at history. I'm not even going to try and look that up right here because I'm recording this live and I just want to put it up raw. So, one of the problems they had up there, and you may think it was just the fact that they weren't used to the gravity and trying to move around was very difficult. No, it wasn't just that. The problem was that they were suffering from static cling badly. So their suits were, dust and debris were clinging to their suits, interfering with the joints and everything, so that they couldn't properly move. That's why they look like they're bouncing instead of walking. Not to mention the low gravity, but that's beside the point. The point is that they couldn't really move the suits that well. Part of it being that static clean was happening, and they had particles all stuck to them. This is further emphasized by the more recent of the touch and go done to the asteroid Bennu. And come to find out, Bennu is not a solid object. It is a bunch of pieces being held together. Well, there's only one way that would happen. Static cling yet again. So the force that's holding stuff together is effectively just static cling. So it's static electricity. It's electromagnetism. Gravity is effectively just another form of electromagnetism. Yes, I know Einstein tried to do that, and he failed miserably, and most people are going to be like, yeah, no, that's not right. Well, that's because you're doing it backwards. You're thinking that gravity creates electromagnetism. Try it the other way around. You're backwards. Now, how exactly to go about that, I don't know, but you've got it backwards. That's why Einstein failed. He tried to fit electromagnetism into his model of gravity, and it didn't work. Well, that's because you're trying to put a result into the process instead of seeing the process and realizing you've got the result. You're saying that the result is actually the first step. Like the first step in the math problem is to write the answer, is what you're doing. Now, the first part of it is to figure out where to start. Like, do we have a plus? Do we have a minus? Do we have subtraction? Do we have subtraction? Do we have division? Is there an exponent? You figure out where to start. That's where you start. And that's not right. That's why I don't like the idea of gravity being like its own entity. You're not going to find gravity just floating out in space. You're going to detect gravity coming from something. Usually it's a planetoid or a star. And with that being said, guess what that means that a black hole is? It's not a flippin' hole. I get so tired of hearing that too. Anyway, so gravity and the particles and everything, yeah, you're not going to find that. It's just not going to happen. And that's been bugging me for like many years now. Way back before I even realized certain things. There's certain things in science that already exist. And I was like, oh, that already exists. Like it was something I was doing with stars, trying to prove certain things within astrophysics, and I was like, I need to find like evidence of this and be like, I need to find like the facts that people have already gathered on stars, because I need to point this out, like show the data and be like, here, right here, look at this. And that was like it was a correlation between the size of a star, the color of the star, and what the star is actually made of, which should in turn tell you exactly the level of fusion, like the energy of the fusion of it, which should tell you the density of the core and blah, blah. Well, come to find out that's already a thing. Yep, that's already a thing. I forget the name of the chart, but it already exists. And the reason I wanted to find that is to try and point out that a black hole is not a hole. You're not going to find a black hole and then somewhere out there in space, oh, look, there's debris and matter coming out of nowhere. Yeah, that's not going to happen. It's like Neil deGrasse Tyson always talking about wormholes. Have you found a wormhole yet? You're not going to. You're never going to find one. Anyway, point is that the truth about a black hole is it's not a hole at all. It is a very large gravity well from, we're just going to say, a celestial body for now, because I don't really think I should call it a star or a planetoid, but there is something there at the core. And one of the things that I kind of thought up with that is that the only way you would be able to ever see it, and we've actually done this is something I thought up a few years ago, and it was done like a couple years ago. I already forgot when they actually did it, and I was like, yep, there you go, there's a proof of what I was saying all along. The only way you would be able to actually see a black hole and photograph it is in the infrared, because the light that has managed to escape from the black hole would have shifted into the infrared. So you now know the limit of how strong gravity could actually be before even light can escape it. There is a limit, like a hard limit. Yes, there are varying sizes of black holes. Trust me, all of them, you should be able to see them in infrared. And if you can't see it in infrared, I know they had to use some special calculation just to be able to photograph one. No. I'm not sure what they needed the calculation for to see that. Maybe it's to make sure that they've got the right angle in order to capture it. I'm not sure what. But if you just look where one should be and filter for infrared, you should be able to see it, regardless of where it is, regardless of the size, regardless of distance. Now, I will admit that that does create a problem. I don't know when the redshift stops. If you don't know what redshift is, okay, we need to talk a little bit about light for a half second so I can explain redshift. So light, we're just going to go with what they still think light is. Light is effectively a wave of particles that is traveling through space, and it illuminates things and bounces off them and blah, 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 blah. But light comes in colors. And over the age of the light particle, or the light beam, however you want to say it, it doesn't really matter. The light particle, light beam starts losing energy. Okay, it does run out of energy eventually. I'm not sure at what color spectrum that would happen. Uh, Again, that's not knowledge that I have ever really thought to even look up, so that's something I probably should look up. But the light beam over time will change color. And what redshift is redshift is when the light is so old, it's traveled so far, and it's lost so much energy. Excuse me, I'm gonna take a drink. That the light particle or light beam itself has shifted into the red of the color spectrum. More correctly, it's shifted into the infrared. Uh, I'm not sure if infrared is the end or if ultraviolet is. I may have those backwards. I'm not sure. And I completely forgot where I was going with that, but you get the idea. Like, once it's in the infrared spectrum, I don't know what it would be after that. So depending on distance and the age of the black hole, it may be shifted into a different color spectrum at that point. I'm not sure. Or not a visible light spectrum. It's a different light spectrum at that point. Or if the red is the end of the life cycle for the particle, then you wouldn't be able to see it at all. Uh, but basically, yeah, there you go. You should be able to see any black hole in infrared, not just one because they wrote some ridiculous formula. Okay, yeah, you should be able to see any of them. Again, if there's any kind of special thing there, I don't know. That is one of my goals that I would like to achieve in the future. Is I would like to take some more advanced courses and everything in college. But yeah, that's pretty much all I wanted to talk about. I can't think of anything else within the science. Oh yeah, the Big Bang. Yeah, yeah. Okay, we need to talk about the Big Bang for a moment. It just dawned on me. I also wanted to talk about that. So let's get out black concrete. Why not? Yeah, we'll do that. We'll just say that this is the Big Bang, and we're not going to get philosophical too much. But there is often the debate that if the universe is a sphere, what would happen if you got to the end of the universe and stuck your hand past it? If your hand still exists, then you should be able to put your back to where your hand is and then extend your hand from there, and so on and so forth. So there should be no end to the universe. Yada yada yada. Basically, philosophical things saying, yeah, that the universe doesn't have any kind of edge. It is never ending and everything. And one of the things that I noticed about it is they always talk about how big the universe is because of the Big Bang and of the expansion. I don't think expansion's a real thing. We'll get to that in a minute. But they always talk about how big it is. And one of the things that I've always noticed is they talk about it and they say the universe is a certain age. And that's why it's this big, because that's as far as light has traveled, and it's still going. However, if you look at their estimated size of the universe, um, it's farther. The distance that light has to travel out that far is further than their estimated age of the universe. And this is something I questioned Neil deGrasse Tyson on X, and I never got an answer back. So maybe he sees this. I don't know. I know he's probably gonna scold me for saying certain things, but whatever. Uh, anyway, so they always do this, and I've always been like, why are you saying that the universe is this old, but the radius of the universe is far larger, far larger. This is something I questioned him about. I was like, why is the size of the universe bigger than the estimated age? Because if light is traveling at a constant rate, the size of the universe should be as big as it is old. They should match up. They don't match up. Okay, so here's my thought on the Big Bang. There was no Big Bang. Instead, this is something I've thought about for a very, 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 very long time. What you think is the Big Bang is a supermassive supernova. A very, very big, we're just going to say explosion, for lack of a better term. It's just a very big explosion. Very, very, very big explosion, okay? That's all it is. Very big. Obviously, we're not going that big with this, but that is all it is we are literally looking at information about a super massive explosion that happened, most likely a supernova of some sort, and thinking, oh, this is a Big Bang. This is what created everything. No. And James Webb is proving that thought pattern incorrect, because if this is the age of the universe, and it's still expanding and everything, and we should be seeing universes like out here that are, a certain way, but instead what we're finding is that they're basically the same as everything else that we're seeing on the inside or closer to home. Yeah, that tells me right there that there was no Big Bang that created all of this, or a Big Bang that created the universe and expansion is still happening. No. Sorry, that's not how that works. As far as the actual expansion goes, there's a quick way that I can demonstrate what expansion actually is. Grab a balloon, and if you don't have a balloon, well, pause and get a balloon. And if you're not gonna be like, oh, I'm not doing. If you're gonna be like, I'm not gonna go grab a balloon, just run this through your head with me. Grab a balloon and start blowing into it. What you'll find is very early on into it, like a few breaths in, the material of the balloon is still somewhat tight. Okay, so it's very dense. In order to, get to a certain size, like the balloon is still very, 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 very dense. Okay, very dense there. But as we go out, you'll notice that the material, as we continue pumping air, is getting stretched a little bit thin on the edges. And, you keep going, and it's going to keep getting thinner and thinner. Like the material is going to keep getting thinner and thinner in every direction, okay? And this is the same thing with why they talk about measurements in certain things, and why you could be billions of light years off if your measurement is off by 0.1 0.0 to the eighth power 1. So that's a lot of zeros in front of that 1 behind that 0.0. Point is like adding it up and everything and going out and out and out and out and out and out. You could be very, very far off from where you originally started. Very far off. Like your measurements are going to be like completely off. Like if you're off by like a 3, like imagine if we were supposed to go that way, 10, let's say 10 trillion blocks that way, and then like every 5 blocks, 1 2 3 4 5, I'm not going to do the math on this, the math is going to be horrible. Every 5 blocks we veer off to the right, every 5 blocks. So by the time we get to that 10 trillion mark way out there, how far away, how off are we going to be? You're going to be very, 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 very far off. Very. Okay. So that is why they think expansion is accelerating. It's because once you start spreading out that far, it's not actually accelerating. It's just, it's expanding further and further and further. There's an actual word that I've just completely forgot. Shoot, what's the word? It's escalating. It's escalating exponentially. Exponentially is actually the word I was looking for, not. So it is expanding exponentially as it goes out, and that means that it's also expanding outward exponentially. So it's getting bigger and bigger and bigger faster. It's like the old mental thing. Like, would you rather have $1,000 today or receive a penny doubled every day for 30 days? Which one would you get? You should take the penny, because by the end of that, you've got, I forgot the actual number, but it's like 3,000 something. It's like $3,000 that you have. So it's a lot more than just taking the $1,000 now. Anyway, so that's why the expansion's like, they think the expansion's getting bigger. There is no actual expansion. What you're witnessing is, I want to say backdraft, but effectively you've got like the back of a sheet of paper that you're looking at. You're not looking at the front side of the sheet of paper. This is where it is. This is where the thing is that's going that way. And that's another thing that I want to talk about with the Big Bang real quick. The what's the actual acronym for it? MBR, microwave background radiation. One of the things that I've noticed with the microwave background radiation, I've seen this for years. If you pull it up, it's all like blue and light and everything, and very, very like cold looking. A lot of blue, a little bit of green, and then you got some places where there's some red in it, and then there's some yellow and everything. But the NBR is very, very interesting to look at, and people are like, oh, this is proof of the Big Bang. This is what's left over of it. And one of the things that I've done a couple of times, I wish I could just pull up an image of it because I've got it saved somewhere. Hang on, I might actually, I don't think I actually have it somewhere where I could just pull it up real quick. I'm not even sure where I saved that out either. Anyway, if you take the MBR, an image of the MBR, and you shrink it down to a sphere, and then you invert the colors, and then you make it warmer because early universe, according to them, was very hot, and then you make the coloration warmer and warmer and warm as your setting will go on whatever editing program you are using, like Adobe, or for me, I use Paint.net because I'm poor. I can't afford Adobe. I wouldn't want it anyway because it's just a whole next level of, I don't know how to use this. I've taken one class on it. Anyway, so if you do that, you're going to end up looking at an almost orange yellow ball. What does that look like? What does that look like? That looks like every textbook image I have ever seen of a star. Yeah, like do it. Like pull up the MBR, pull up an image of it, and then shrink it down so that it looks like a sphere. It doesn't have to be perfect. It just gotta look spherical. And then invert the color of it. You may have to delete the background. Okay, we got this solved. So, like I was saying, if you take the CMBR or the MBR, the cosmic microwave background radiation, and you do some quick edits to it, like invert the colors and everything. Well, first let's talk about this. So, what you're seeing is basically what they think is left over from the Big Bang. And this is everywhere. This is how the whole universe looks when you're doing like when you're taking certain measurements. I don't fully understand it and everything. However, it's the color thing that I wanted to point out. The first thing that I noticed looking at this is if this is after the Big Bang, and all of this is cold, why isn't it as warm as it should be? Well, that's because we're looking at it from the wrong side, and it's been a very, 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 very long time since then. So yeah, it has cooled off. And that also means that with that, you got to think about, the light has also changed. So we need to revert this back. We need to invert it and then bring it back to a certain look and everything. This is not going to be perfect because this was quick and easy, but this is a CMBR as we've been shown, as most scientists probably know it as. I'm not exactly sure. However, again, color theory, invert all the colors and then warm it up even more. So we get something that looks more like this. And I have made it as circular as possible. Now, I can also like decrease the size here to make it a little bit smaller, so it's a little bit more dense. But what you get is a much more red sphere, which looks pretty much like any star that I've ever seen in my entire life on anything, like any kind of video or any kind of science documentary that talking about stars and everything. Like I'm trying to think of one of the scientists that just bugs me anytime I hear him speak. I don't like how he speaks. He's very knowledgeable. It's just his speech pattern just bugs the heck out of me. Uh, he's very drawn out and slow and everything. It's just kind of like, can you talk any faster, please? Anyway, like I said, this looks like any of those stars I've ever seen. Now, it does have a good chunk of blue in it, but you also got to remember that any kind of blue is actually way hotter than red, way hotter than yellow. So yeah, it's not exactly right. You got a couple different colors going on there, but again, that's all color theory, and it would take somebody doing some precise changes and everything to make it like a hot, dense area like they think the Big Bang was. It wasn't. It was just another star that exploded. That's the point I'm trying to make here. But yeah, that is what the CMBR actually looks like if you invert the colors and shrink it down to a spherical shape. And that's always bugged me that nobody's ever thought of doing that. Like, I can't find any evidence anywhere of anybody ever doing that. And even the first time I looked at it, I was like, invert the colors. Because what you're looking at is not entirely correct. All of this is not entirely correct. Like, but even this, you need to be able to measure that at several different points. And if these particles are changing only except for when you measure it, then you should be able to catch it in the act of changing. Again, you would have to set this up so that you could catch this, but the point remains you should be able to measure it multiple times and then be like, aha, look, these are different. And then that would be like, oh, okay, so they are changing. It's only when we check them that it has changed. Like, one thing I would love for them to do is actually take this too and like take a measurement in front of these and see what it is, because it should correspond. You should still see that these are a certain thing. Like, definitely take a measurement of it. Anyway, that's kind of some of the stuff that has been on my mind for a while and thoughts that I've had, and just wanted to share that. I know it's kind of weird that it's in Minecraft. uh, there's reasons for that, and again, that one of those was just to show the level of thought input and my process of understanding things that I should have no business understanding. It's even like all the star talk and everything. Like, it's it's not that difficult to understand. I don't know why people freak out over it. I have several books by Neil deGrasse Tyson and others. Anyway, that is what I am going to leave you with. And actually, finishing thoughts on all that. The whole reason why relativity and quantum mechanics don't get along is because there's a size difference. This is something like somebody whined about online because I said this somewhere. There's a size difference. You don't measure something. Let's just make something quick here. you wouldn't measure these two things the same way because there's a size difference. And because there's a size difference, they also function differently. Yes, I know that's a button, it already functions differently, but imagine that's just a small piece of wood. Because there's a big difference in size, these function differently. The best example I can give of that is the difference between what happens to an ant and an elephant if we were to drop it from atmosphere. According to pretty much anybody out there, the same thing should happen to both, but that's not actually what happens. The ant is so light that it gets carried on the wind and it goes somewhere. Hopefully, basically, if there's nothing really bad, like it doesn't fall in a lava pit or drowned in the ocean, it's going to fall to earth and then crawl away. You drop the elephant from that distance and you're going to have a bloody mess. Yeah, size matters, people. That's the reason why these two don't get along, because size matters. General relativity measures very, very big things. Quantum mechanics measures very small things. The two are not going to work well together. My best example of this, and I've been trying to find her research for like forever. I don't even remember her name at this point, but there was a scientist who had decided that she was going to do this from the direction it should have been done all along ago. She was going to start at the bottom, at quantum physics, and work her way up to what we consider general relativity. And the proof of what I would like to say about why she was right on this stuff is to do with black holes, because she came to the conclusion based on that, all that measurement and all those calculations and everything, that the black hole is one of two things, and I can tell you it's not one of them. The two things are, it is either a very small hole that is spitting out stuff into nowhere, which, yeah, I already said that it's not that. And the other one is that a black hole is a huge gravity well with a very, very small item in the middle of it. Frankly, her measurements say that it's very tiny, like it's absolutely tiny. I don't think that's right. I do think it would be very dense. It would probably be the most dense object in the entire universe. And depending on the size of the black hole, depends on how dense the item is. I imagine there is a point of no return, though. Once you get stuff compacted so much, it can't be compacted any more than that, basically. Same thing for light speed. Like once you go so fast, you can't go any faster. The same thing with density is once something is so dense, there is no compacting it anymore. You can't get any more dense than something. It's very funny that I'm talking about being dense and everything, and we've been spilling off stuff, and somebody's probably going to leave a comment being like, "Yeah, you're dense." I can just see that happening. Anyway, I'm the Tennis Lycans, and subscribe. My channel's dead. Why am I saying that? Anyway, y'all be good. I'll see you later. Bye.